Good morning, dear students. Today we shall see the potential energy of the elastic solid expressed in terms of the global stiffness and load matrices. In the previous class, we saw how a global stiffness matrix was prepared, assembling the stiffness matrices of all elements. Now, we shall see the global load vector F. F is the global load vector that takes account of the element traction vectors, element body force vectors, and concentrated forces, where F is the global load vector that takes account of global body force vector, global traction vector, and concentrated forces. We know that here the global traction vector is the vector that results from the assemblage of element traction vectors. Global body force vector is the matrix that results from the assemblage of element body force matrices. We know that the element body force vector Fe, which equals to F AE LE by 2 into a column matrix having the elements 1 and 1. This is the expression to determine element body force vector. Next, element traction vector, right, which equals to, we know that T LE by 2 into a column matrix having the elements 1 and 1. Remember here in this expression F is the body force. F is the body force per unit volume, right? For every element, the body force per unit volume is constant. In this expression, T is the traction per unit length. For every element, the traction per unit length is constant, right? Now, what is AE here? The cross-section area of the element, and what is LE? Length of the element. Okay. Now, if you take an elastic solid and discretize the elastic solid into finite number of elements, for each element you have to determine element body force vector. For each element you have to determine element traction vector. Okay. Then, assemble the element body force vectors. Then you get the global body force vector. Assemble element traction vectors, then you get global traction vector. After getting the global body force vector, global traction vector, right? Then sum up the global body force vector, global traction vector, and the concentrated forces. You get the global load vector F. F is the global load vector. So, how you understand the global load vector F? It is the vector that results from, right, the sum of global body force vector, global traction vector, and the concentrated forces. Understand carefully here. The sum of Fe, it gives you the global body force vector. The sum of Te, it gives you the global traction vector. Okay. Now we shall see how the global body force vector results from the assemblage of element body force vectors. Okay. I take an example and explain. So firstly, we prepare the global body force vector. I take a solid like this, right? So here the solid has one step. The solid has one step. The solid has one step, right? One end is fixed. Other end, is carrying an external force like this, as shown. Now, the cross-section area of this part is, say, A1. Length is L1, Young's modulus is E. The cross-section area of this part is A2. Length is L2 and the Young's modulus is E. Right? Now, if you observe this part which has uniform cross-section, this part also has uniform cross-section. But here, at this section, the cross-section area is abruptly decreased. Okay? Therefore, we can model this entire solid with two finite elements. From here to here, I take the first element, and from here to here, I take second. Okay. Now, if you give node numbering, I say this is the first node, this is the second node, and this is third node. Now, the element connectivity information I give you. Node 1 is the first node of first element, node 2 is the second node of first element. Node 1 is the first node of first element, node 2 is the second node of first element. Next, for second element, node 2 is the first node and node 3 is the second node. This is the element connectivity information. Normally this we tabulate. This we tabulate. Okay. When you solve a problem, you have to make a table giving this information. Next. So here, what is my first interest? My first interest is to prepare global body force vector. Now I define. This is, the body force acting over the entire volume of this element. And this is the body force acting over the entire volume of the element. When the solid is made of same material, right? I define, say F is the body force per unit volume. This is same for element 1 and also element 2. F is the body force per unit volume. Right? It is the body force acting over the entire volume of the solid. Therefore, for each element, it is the body force acting over the entire volume of the element. Okay? Now, so what is the expression for the element body force vector? Fe, Ae, Le by 2 into a column matrix with 1 and 1. For first element, I prepare body force vector. For first element, I say F1 is equals to F A1 L1 by 2 into a column matrix with elements 1 and 1. Remember, these correspond to the first and second degrees of freedom. Right? The first degree of freedom. See, when I take x-axis like this vertically downwards with coordinate origin here at node 1. Okay. Node 1, right, tends to move in the direction of x-axis. Therefore, I say this is capital Q1. Of course, upper end is fixed, therefore Q1 is 0. Right? That is, a different, matter. Next. Node 2 tends to move in the direction shown. And coming to node 3, it tends to move vertically downwards. Therefore, its displacement is Q3. So, Q1, Q2 and Q3 are the global displacements. Okay? Right. Therefore, I say F-A1 L1 by 2 corresponds to first degree of freedom, and again F-A1 L1 by 2 corresponds to second degree of freedom. Okay. Now if you take this inside, then what you get? You get a column matrix, very simple. F A1 L1 by 2, F A2 L2 by 2. And these correspond to first and second degrees of freedom. Right? Next, for second element, what is the element body force vector? F2. This equals to, again, straightly I write a column matrix having the elements F A2 L2 by 2. Next, F A2 L2 by 2. These correspond to the second and third degrees of freedom according to the element node connectivity information. Now, when you assemble these, you get the global body force vector. It is a column matrix. It is a column matrix with number of rows equal to the total degrees of freedom of the domain. How many degrees of freedom are there in the domain? 3. In the domain, there are 3 degrees of freedom. What are they? Capital Q1, capital Q2, capital Q3. Hence, if you prepare the global body force vector, the global body force vector I denote by, say, capital FB, B for body force. Right? It is no doubt a column matrix with the number of rows equal to the total number of degrees of freedom in the domain. Therefore, what is the size? You are getting here simply 3 by 1. Rows you get 3. Right? So, how you make? Let us see. This I take F1. Right? It is a column matrix with how many rows? 2 rows. Now, what I do is I consider here the third degree of freedom. Right? I put 0 here. You don't have any problem. Understand? Now in this, what I do is, in this, I consider first node also like this. This is the first degree of freedom. Then what is the corresponding element? I put 0. I don't have any problem. Right? Now, to determine the global body force vector FB, what you do is, simply sum up these two matrices. Then how you get? A column matrix like this. Right? What are the corresponding degrees of freedom? Q1, Q2 and Q3. Therefore, I write 1, 2, 3 here. Now, when you sum up, what is the element in first row and first column? It is simply F A1 L1 by 2. Next, coming to the element in 2 by 1 location. Tell me what it is. F1 A1 L1 by 2 plus, not F1, it is F. Please make correction. It is F, not F1. F A1 L1 by 2 plus F A2 L2 by 2. Right? Understand? Okay? This is, you make correction here. F A1 L1. It is not L2. F A1 L1. Okay, na? Right. Now, if you add F A1 L1 by 2 plus F A2 L2 by 2. Next, again. Now, if you add this to this, then what you get? F A2 L2 by 2. This is the global body force vector. Global body force vector is a column matrix with number of rows equal to the total degrees of freedom in the domain. Okay. This is how we prepare. Right? If there are n degrees of freedom, then what is the size of this global body force vector? Then the size of the global body force vector becomes n by 1 if there are n degrees of freedom in the domain. This we have to understand. Right? Next one. What we do is we take traction again. We take traction. Okay. We take traction now. We take traction and prepare the global traction vector. Again, what I do is I take again the same problem. Okay. I have an elastic solid with two abrupt changes in cross section. This is the force acting vertically downward. This is first element and this is second element. The cross section area of this is A1 and its length is L1. The cross section area of this is A2 and its length is L2. And entire solid is made of same material, therefore Young's modulus is same for both parts, for both elements. Now I consider axis X vertically downwards. This is node 1, this is node 2 and this is node 3. Okay? Now this is the displacement capital Q1, this is the displacement capital Q2 and this is the displacement capital Q3. Right? We use the same element node connectivity information. Right? Now, traction. I take surface traction. Right? Surface traction it is. Traction is T. Like this. Traction is T. It is written by T. It is the force per unit length. Okay? Now, what is the formula for determining the element traction vector? It is T LE by 2 into a column matrix with elements ones. Therefore, for first element I write T1. For first element T1 equals to, see, it is a column matrix. Right? For first element I write simply it is T L1 by 2 here, T L1 by 2 here for first element. Okay? For first element. Now these elements correspond to the first and second degrees of freedom. Next T2 I write element traction vector for second element like this. Right? For second element, tell me, what is first element? T L2 by 2 and second element is T L2 by 2. Okay. What are the corresponding degrees of freedom? 2 and 3. Okay. Now, I prepare the global traction vector. So that is capital T. What is the size of global traction vector? The size of global traction vector, right, depends on the total degrees of freedom in the domain. Global traction vector is a column matrix with number of rows equal to the total degrees of freedom of the domain. Right? Therefore, what is the size? It is 3 by 1. Hence, the elements of this matrix correspond to the 3 degrees of freedom. Hence, I write 1, 2, 1, 3. Okay? Now, what I do is, here I don't have the element correspond to 3rd degree of freedom. Hence, I write 3 here, I put 0 here. And here there is no element corresponding to 1st degree of freedom. Therefore, I write 1 here and put 0 here. Simply sum up. Because the sizes of both matrices are same. Simply sum up. Then what you get? Here you get T L1 by 2. And next one T L1 by 2 plus T L2 by 2. Next here T L2 by 2. This is the global traction vector. Okay. Now, global load vector F we have to prepare F. I told you the global load vector results from the assemblies of global body force vector, global traction vector and concentrated forces. Right? In the previous example, we have prepared the global body force vector. The global body force vector and this global traction vector. Next, the concentrated force. You have to sum up. Then you get the global load vector. How we get that also we see now. Right? That also we see now. How you get? I draw the figure first. Easily you can understand the same figure I draw. This is my figure. Okay, this is the configuration. Force F is acting here. This is node 1 and this is node 2. This is node 3. Origin of the reference frame is here. X-axis is taken vertically downwards. When you take x-axis vertically downwards, the force F is positive. This is first element and this is the second element. So this is the traction P, and consider the body force also. F is the body force per unit volume. Right? The global body force vector we obtained like this. FB equals to, we had the global body force vector like this. It is a column matrix, right, of size 3 by 1. So what are the corresponding degrees of freedom? 1, 2 and 3. Okay. What is the first element? The first element is, F A L1 by 2. What is the second element? F A L1 by 2. Not A it is A1. F A1 L1 by 2. Here F A1 L1 by 2 plus F A2 L2 by 2. And here F A2 L2 by 2. We have the matrix like this. Right? Next. Global traction vector capital T. It is also a 3 by 1 matrix. What are the corresponding degrees of freedom? Q1, Q2, Q3. Hence I write 1, 2, 3. Okay, what is the first element? Element in 1 by 1 location. Now, the first one is, it is T L1 by 2. Right? L1 is length of the first element. Length of the first element. I write here E A1 L1. So here E A1 L1. Next here E A2 L2. Okay. Right? T L1 by 2. Second element. Tell me it is T L1 by 2 plus T L2 by 2. And here element in 3 by 1 location T L2 by 2. Okay? So concentrated force is acting at the vertically downwards. Therefore F is positive. Now we want the global load vector capital P equals to the global load vector. Right? I say capital. Global load vector. Global load matrix. What is its size? Its size is also same, 3 by 1. Right? Therefore, I write a column matrix. Column matrix. What are the corresponding degrees of freedom? Q1, Q2 and Q3. Therefore, I write 1, 2, 3 here. Now, sum up simply. F A1 L1 by 2. Next, plus T L1 by 2. Next, Any concentrated force is acting here at node 1? No. If it is acting, for example, vertically downwards at node 1, then plus put that load. Because no force is acting at node 1 in the direction of x-axis, it is 0. Right? Be careful. If a force is acting at node 1 vertically downwards, then plus put that force. If a force is acting at node 1 vertically upward, for example, then put minus that value. Right? Because the positive coordinate axis is taken vertically downwards, the forces acting in the direction of x-axis are positive. This is the sign convention. Then the forces acting vertically upward, negative. Okay? Now, next. Tell me F A1 L1 by 2 plus F A2 L2 by 2, next plus T L1 by 2 plus T L2 by 2 plus any force is acting at node 2 vertically downwards? No, so 0 plus 0. Right? If any force is acting at node 2 vertically downwards, if it is acting at node 2 vertically downwards, then we put plus that value. Okay? Right. Next, node 3. Simply, what do you get? F A2 L2 by 2 plus T L2 by 2, right? Plus, at node 3, F is acting, therefore I put plus F. If F is acting at node 3 vertically upwards, then you put minus F. This is how one has to prepare the global load vector. The global load vector. Very, very important. Right? You have to prepare the global stiffness matrix capital K. Then you have to prepare the global load vector P. How this global load vector results from, right, the global body force vector, the global traction vector, and concentrated forces acting at respect to nodes of the domain. Okay, right. Now, okay, this is the global load vector. This is the global load vector. In our discussion, this was taken as P in our discussion. Because in the solid, I took a force F acting at node 3. Therefore, in my discussion, I took this as P. Okay. But here, F we take as the global load vector. Once you get this and also this, we can represent the total potential energy like this in terms of the global stiffness matrix and global load matrix. Okay. How we write? Pi equals to 1 by 2 into capital Q transpose into capital K into capital Q minus capital Q transpose into F. Remember, if there are n degrees of freedom in the domain, if there are n degrees of freedom in the domain, then what is the size of Q? What is size of K? What is size of Q transpose? We know that capital Q is the global displacement vector. It is a column matrix. We define it as a column matrix. Therefore, how you write? You can write it as the transpose of row matrix for convenience. Hence, what are the elements? Q1, Q2, Q3 and so on, so forth. It ends with Qn transpose. Right? We write like this. When there are n degrees of freedom in the domain, be careful. Okay? N degrees of freedom in the domain. Right? Now, what is degree of freedom here? Displacement. Right? Displacement. Now, what is the size of Q here? The size of Q you can write here. Tell me, what is the size of Q? The size of Q is here n by 1. Size of K n by n. Right? And size of Q transpose. Size of Q transpose. It is 1 by n. Okay. Now observe carefully, the product of these three matrices is possible. 1 by n, here n by n, n. Okay. Right. And what is the size of Q transpose here? 1 by n. And what is the size of F here? N by 1. Understand? This is how we can represent the total potential energy in terms of the global displacements, global stiffness matrix, and global load vector. Right? Okay. Now, once you get the total potential energy pi like this, then what you can do is, you can extremize it. You can extremize it for determining the equations of equilibrium. Right? Okay. Next. Properties of K. What is capital K? I told you capital K is the global stiffness matrix. Global stiffness matrix. Capital K is the global stiffness matrix. How it results? Global stiffness matrix results from the assemblies of all element stiffness matrices. Okay. Now, global stiffness matrix capital K is a square matrix. We had discussed in the previous class. What we had discussed, I took an elastic solid like this with one end fixed end, right? An elastic solid like this with one end fixed end, and other end, carrying a force F vertically downward. This is first element, and this is second element. What is Young's modulus E? Cross section area A1. What is length? L1. Young's modulus E, cross section area is L2, length is L2. Okay. Entire ball is made of same material. Therefore, Young's modulus is same. Okay. Now, how you prepare the global stiffness matrix? First you have to determine the element stiffness matrix for the first element and element stiffness matrix for the second element. Right? For first element, K1. Right? What is the formula? You know it. E A1 by L1 into a 2 by 2 matrix with 1, minus 1, minus 1, plus 1. What are the corresponding degrees of freedom? Q1 and Q. Therefore, I put 1. And for second element, what is K2? K2 equals to E A2 by L2 into a 2 by 2 matrix with elements 1, minus 1, minus 1, plus 1. What are the corresponding degrees of freedom? 2 and 2. This is node 1. This is node 2. And this is node 3. Right? Now you assemble these two, you get global stiffness matrix capital K. That I tell you now. Capital K equals to, here Young's modulus is same, therefore I keep it outside, E into. As I said, the global stiffness matrix here is a 3 by 3 matrix, because the size of the global stiffness matrix equals the total number of degrees of freedom of the domain. Right? Now, how you get the corresponding degrees of freedom are Q1, Q2, Q3. Therefore, I write 1, 2, and 3 here. You get the element in 1 by 1 location, that is, A1 by L1, you know it. Here you get minus A1 by L1 because E is outside now, E is common. And you get 0 here. And here you get minus A1 by L1. Okay, here you get A1 by L1 plus A2 by L2. Here you get minus A2 by L2, and here you get 0, here you get minus A2 by L2, and here you get A2 by L2. This is what we had in the previous class. Global stiffness matrix capital K. How it looks? A square matrix. So global stiffness matrix is a square matrix. That is the first property. It is a square matrix. Understand? And it is also a symmetric matrix. It is also a symmetric matrix. Let us see. For any matrix, if Eij equals to Eji, it is said to be symmetric. Hence, see here, this is the element in first row and second column. Right? First row and second column. This is the element in first row and second column. Now we take the element in second row and first column. This. Both are same. Both are same here. This and this both are same. Right? Now I take element in third row and first column. Third row and first column 0. Now I take element in first row and third column 0. Both are same. So here the condition Eij equals Eji is satisfied. Hence the matrix is symmetric matrix. This is another property. Global stiffness matrix is a square matrix and it is a symmetric matrix. Size of the global stiffness matrix equals to the total degrees of freedom of the domain. Another property. Next property. Here, because it is symmetric, right? You need not store all the elements in the computer. Okay. You need not store all the elements in the computer. The elements that are contained in the band you can store in the computer. What is the band here? Let us see. Let us see. What is the band here? Let us see. Now, this is the band. Observe carefully. This is the band. If you store these elements, in the computer, they are enough to make computations. You need not store other elements. You need not store other elements. Right? The global stiffness matrix is banded because the elements outside the band are zeros. Understand? The elements outside the band are zeros. You need not store all elements. Right? You need not store all elements. The elements outside the band are zeros. Therefore, the global stiffness matrix capital K here is a banded matrix. K is banded. If you take three elements, here I have taken only two elements. If you take three elements, right? And give node numbering 1, 2, 3 and 4. With element node connectivity information, say node 1 is the first node of first element, node 2 is the second node of first element. Next, node 2 is the first node of second element and node 3 is the second node of second element. Next, for third element, node 3 is the first node of third element and node 4 is the second node of third element. With this information, if you prepare, right, the global stiffness matrix and observe K banded, you get like this. K banded, you get like this. K banded, you get like this. Understand? Today what we have learned? Today we saw how a global body force vector is prepared, how a global traction vector is prepared, and how a global load vector is prepared, and how the potential energy is expressed for an elastic solid in terms of the global load vector and global stiffness matrix. And later, we also have seen the properties of global stiffness matrix. Okay? Thank you. Thank you very much.